Right. Hi. I do realize I'm the only thing standing between you and cool conversations over coffee, so I'll try to be quick. So this is basically the phase one, sort of a proof of concept idea about the possible application of underwater cameras or microphones and doing like hazard early warning, including earthquakes. For the purpose of this talk, I'm going to be focusing on the sequence of earthquakes happened in the Persian Gulf region in past June and July. So here's where we are. There's the Persian Gulf. In the north, you have Iran. In the south, you have the United Arab Emirates, and that's where the football is. There's an ongoing continental collision between the Eurasian plate and the Arabian Shield, which has resulted in a huge amount of earthquakes, 99% of which are on the Iranian side of the isle. And this little blip here is the Quiche Island that we're going to focus on for the rest of this talk. Now, this is the sequence in question. It started somewhere in mid-latitude and then migrated sort of to the west, then sort of migrated back with a magnitude 5.6, a couple of aftershocks, then eastward with a bunch of magnitude 6s. Of course, the whole quake storm. There are three clusters, obviously. I'm going to be focusing on cluster A. Now, some features of this cluster, there were more than 130 earthquakes. The largest of which was magnitude 5.6 on June 25th. The biggest one, along with a couple of other guys in the cluster, were felt all across at least the entire eastern Persian Gulf. There are reports from citizens in Dubai reporting moving furniture, strong shaking, and that sort of thing, which is kind of bonkers because if you look at it, it's more than 170 kilometers away from the epicenter. It's kind of crazy. So the question is, what's causing all of this? There's also, admittedly, a location uncertainty associated with this event. So here, I'm showing circles are showing earthquakes. They're color-coded according to earthquake source slowness parameter. And what this tells me is that a majority of these sources are actually very, very high frequency. Stars also show the epicenters from published epicenters from the various agencies here. So here you have USGS and CNT are pretty close to one another, and there's 20 kilometers south, you have the ISC and the IRSC, which is the Iranian Seismological Center, and then you have also another one, the white star here. So this is basically a shotgun blast. And an interesting thing happened during this earthquake. A bunch of divers were scuba diving northeast east of the Quiche Island. I'm sure at this yellow star, this is the Quiche Island. And they made this peculiar recording, which is accessible on Twitterverse, of course, where else? And I'm going to show you the recording, and I'm also show you the time series from the audio track of the recording along the spectrogram from that. So here, when you listen, you hear the diver. There is that noise from the water tank, bubbles, currents moving around, and sort of thing. But around the 17-second mark in the video, this. So there are several features interesting in this video. First, the dominant frequency of this thing is somewhere between 40 hertz and 75 hertz, which is kind of interesting. Then there are a bunch of booms, at least 8 distinctive booms in this series. I'm showing the booms with different indices of B, the largest of which is B5. They're not periodics. They don't appear in any particular order. During B5, the maximum intensity falls to about 45%, 50% of the entire envelope. The main signal has a long duration of 29 seconds, which is kind of odd for a source time function of 5 seconds. And there's a sharp start at the beginning and a spindle shape at the end, and the fish are undisturbed. All of this tells me that this is an acoustic signal. These are not waves from explosion. These are not gravity waves, and of course, they're not hydroacoustic overtones because they're not periodic. So what can we learn from here? The Persian Gulf is this huge geographic basin with an average depth of 30 meters. The median is about 15, which is pretty much like a huge geographic bathtub. if you think about it that way. And this makes it the perfect host for trapped acoustic signals. And these are not news in that neighborhood. They've been popping up in this in the oil exploration seismic sections for forever, but they're all active source. What about earthquakes? Well, if you put in an earthquake source, this is like the simplest approach to do this. If you put in an earthquake source at the depth of H, there are two ways to propagate energy from right to left in this panel, and one is both seismically, of course, S&P waves, and the other one is acoustically. You shoot up a ray, and thanks to the very, very high velocity gradient, it's going to be near vertical refraction. And again, thanks to a very large Q, there's a pretty good chance that it's going to go supercritical real quick after a couple of bouncing up and down. And you can analytically, for a flat seabed, calculate dominant frequency and the group velocity real easily. So for example, if I plug in the typical, the average frequency from our video is going to be 57 Hertz. And this gives me the average water depth of 25 meters, which is very close to what you get from bathymetry data. And remember, the Persian Gulf is pretty flat. Now, admittedly, in the presence of inclined bathymetry or irregular bathymetry, this becomes much more complex, but you can always solve this numerically with minimal problem. Which is exactly what I'm doing here. So for the case of the Persian Gulf, if you remember this map, I'm showing here the bathymetric profile along this white transect here at the bottom, and I'm showing you here up on top. I marked the location of divers and the epicenter from the earthquake. This is just nominal for the purpose of comparison, location comparison. And here is an example of one of our quote-unquote ray tracing simulations. I've just flipped the map on its side. The energy is propagating from left to right. And what I'm showing here is going to be 3 acoustic phases, 2 from PNS converted to acoustic at the location of the receiver, 1 at the epicenter, which we're going to call T, just creatively enough. There is sound on it. I was hoping if you could hear the changes in frequency, which is definitely a function of slope and bathymetry. There are a bunch of interesting features in this. One is that, well, it has a typical duration from start to begin of finish about 25 seconds. The dominant frequency on average is about 50 Hertz. And there are stagnant acoustic signals, meaning the PNS, the acoustics from PNS just keep going back and forth forever, trapped there because of where they're converted. And the direct T arrival is fifth. And now if I put this to use, if I'm ready to buy that the first 2 are PNS and the 5th one is the acoustic signal, I can use typical velocities for PNS and what I get from our simulation. And this is the distance, look at the epicentral distance, which are pretty close, about 600 meters from each other, which is great for an out of the edge of the network event. Now, you can see that this coincides perfectly almost to the IAC epicenter. Also, like in terms of hazard analysis, you can see from the typical shaking, from attenuation equations, nothing's going to happen in the Emirates site. But if I do the indirect quote-unquote shaking, I can see that this is a typical arrival of T-phase, and this is what probably people felt in Dubai. And this needs to be taken into account in doing any kind of hazard model over there, because it's a very high frequency. And finally, in terms of early warning, how can we do this? Well, this is a population map of the region. And I've marked the earthquakes there. One approach would be like smart cables. There are tons of telecom cables over there. You can just put real cheap microphones on the repeaters. And there are advantages to this. There are going to be no power or communication issues, but it's going to be expensive. There are going to be logistic issues. This is the ship track map. You can see that they coincide pretty well. So you have to be careful. And this is long term. But the other approach that we are sort of pursuing also is that, well, hydrophone boxes, you can just put really like condenser mics in a box, insulated with a battery, just dump it somewhere in 20 meters depth. The divers, local citizen scientists can do this for you. It's going to be very, very cheap. There is going to be a time issue. It has to be retrieved, but it could work, at least on the short term. So at the bottom line, as we just all saw today in the great talks, Shake Alert and Raspberry Shake and these things are in hands of citizen scientists. We have done excellent science with them, but offshore, we don't have a single data point. And this is going to remedy a lot of things that we have for out of the edge events. And this is where we are proposing HBox, like creatively enough, hydrophone box. So I'll stop here. I'll be more than happy to take any questions if you may have.
Great. We might have time for one quick question. For rounding the session out again, you know, Amir standing between coffee, but you know,
Yeah.
between the coffee break. So.
Bruce.
Eric, good talk. Are you saying then the people on the other side is, where was it? Anyway, they felt a lot of shaking. Was that the T phase hitting the land on the opposite side?
Yeah, that's what we understand.
Okay.
They admittedly they arrive much later because they travel much slower. The typical velocity is 1.2 kilometers per second. It depends on the bathymetry, but they're very high frequency, and most of the reports or most of the headlines were people in the high rises. So of course it's going to be dampened on the high rise, depending on how many floors you have and all that. But it's very, very high frequency is going to produce a lot of shaking. Sometimes people mistakenly, including the people on the Quiche Island, just assume this is a very, very long earthquake, like lasting for a couple of minutes, whereas they were just getting the PNS and then the T.
Great, thank you.